hopefully everyone just got that notification. So, oh, I saw in the chat, Marshall, let's see. Great, thank you. Yes, I will do that. So welcome everyone to the January instance of the Neptune Triton System Seminar Series. Today's speaker will be Corey Cochrane. So I'm going to switch my slide and allow him to share his. Hopefully that worked. And then while he's doing that, I can sort of introduce him. Let's see, so, alrighty, so Dr. Corey Cochrane received his PhD from Penn State University and worked briefly for Boeing as a satellite communications systems engineer before starting work at NASA's Jet Propulsion Lab with the Advanced Optical and Electromechanical Microsystems Group, where he works now. Dr. Cochrane's research has focused primarily on the development of next-generation instrumentation and signal processing methodologies, which can aid in the measurement and study of planetary magnetic fields and plasmas. He serves as an investigation scientist for both the Europa Clipper magnetometer and the plasma instrument for magnetic sounding on Europa Clipper. He also served as a science affiliate with the Triton Discovery mission concept, developing algorithms for subsurface ocean detection at Triton on a single pass using magnetometric measurements, which he'll be talking about today. So thank you so much for joining us today. And so for anyone in the audience, you can feel free to ask questions through the chat. Corey can either answer them during his talk, or we can save them for afterwards. So you can feel free to post them there. So I'll turn it over to Corey.
Thank you, Jody. I really appreciate being here. Yeah, again, my name's Corey from Jet Propulsion Laboratory. This work was actually funded under the Triton Discovery mission concept, which most of us are unfortunately aware that was not selected to continue in the discovery contest. But this mission concept was highly rated, and our prime objective of ocean detection was actually given a major strength. So hopefully this work can be used as a stepping stone for future mission investigations to this system. And I just do want to give you an apology if you hear any background noise due to the COVID outbreak. Their daycares are closed, so my kids are at home, so they're screaming in the background. So if you hear them, I apologize for that. Having a little PTSD from the last 2 years working and doing, taking care of them, but hopefully this will go smoothly. So while this is a Triton and Neptune focused venue, I'm not going to focus too much on why we think Triton is thought to be an ocean world, but just to remind everybody, Triton is likely a captured Kuiper belt object based upon its orbit and composition. And its high inclination results in significant obliquity, which is predicted to provide sufficient heating to maintain an internal liquid ocean. And it's also got a diverse set of geological features. It's got smooth plains, cantaloupe terrain, and active plumes, which may or may not be associated with a subsurface ocean. And it's also got some indication of some resurfacing via cryovolcanism. So how does one discover oceans if you cannot see them? So this came from the Galileo magnetometer. There's been a lot of motivation using the same technique called magnetic induction to search for hidden oceans and other planets or moons in the solar system using this concept. Over to the right, we see the magnetic field traces BX, BY, and BZ of two particular passes of Callisto, the C9 pass on the left, and on E14, Europa pass on the right. And this blip you see in the middle on each of these three traces is representative of an induction response. A magnetic induction response from a subsurface ocean was first proposed by Margit Kibbleston and Krishan Khurana and others to explain the data collected on these passes, as well as some of the other passes near these moons. And they were able to show that this magnetic signature is effectively time synchronized to Jupiter's rotation period. And what this means is that if you encounter these moons at a different instance in time or a different Jupiter phase, then the signatures will change shape. So this exciting results forms the basis of the Europa Clipper mission and JUICE investigations, which have goals of ocean detection and characterization over the course of multiple flybys. But our goal for Triton was to determine if you could actually detect an ocean on a single flyby. Okay, so what are some of the difficulties of single-pass ocean detection at Triton? Well, my biggest concern going into this is if there could be an internal magnetic field from a self-sustaining dynamo. And a lot of the team members were convinced that we cannot be certain of this, but it's thermodynamically not likely, just due to the small size and likely cooling of the core of Triton. And therefore, convection would not be effective to create this dynamo effect. Also, from Voyager 2, we were able to determine that it's got an intense ionosphere, which could mask an ocean response from an ocean. Because the ionosphere is conductive, it too will react to a time-varying magnetic field and create an induction signal. Also, the uncertainty in the plasma interaction fields from magnetospheric currents. Because of the large variation in the moon's distance to Neptune's central plasma sheet, there could be a 3-order magnitude variation in this plasma density. However, based upon the Voyager 2 measurements, this density is relatively small compared to the other moons, so we don't think it's going to be a problem. Additionally, the uncertainty of Neptune's magnetic phase. I'll talk about this in a little bit, but because the orbital wave and the synodic wave are roughly equivalent in order of magnitude, there could be constructive interference between both of these waves, which could reduce the induction response. Additionally, because Triton is actually quite far from Neptune, even though Neptune's got a strong magnetic field, it's far enough away such that the magnetic field that's observed is on the order of maybe 10 nanoteslas at most. So any induction signal will not exceed that amplitude. And that's actually relatively small amplitude compared to something like Europa, where the induction response is on the order of 250 nanoteslas. Okay, so real quick, I just want to go over the phenomenon of magnetic induction. And obviously, it's based upon Faraday's law of magnetic induction. And this equation basically states that anytime you have a time-varying magnetic field, dBTT, a changing magnetic field, this is associated with an electric field. Take, for example, this simple circuit to the right. We have a coil and a stationary bar magnet. Obviously, if the bar magnet is stationary, there's not going to be any current going through the coil. But as soon as you start moving this bar magnet in and out, this coil senses this changing magnetic field and will drive an electric field that is synchronized to the motion of the bar magnet. This will induce a current that induces a magnetic moment that is synchronized to the driving field and exhibits an amplitude response and phase delay that depends upon the properties of the conducting medium. For the case of a perfectly conducting coil, we'll have an amplitude response of 1, a phase delay of 0, and these two parameters define what we call the complex response function of the medium. Now, for the case of Europa, we have the same thing. We replace this time-varying magnetic field with Jupiter's time-varying magnetic field. And essentially, this drives electrical currents within any conductive layers within the moon, for example, a salty ocean. And this will induce a magnetic moment. But the amplitude response is not necessarily going to be 1. It'll be less than 1. And the phase delay is not going to be 0 because it's not a perfect conductor. And this magnetic moment creates a dipolar field that can be sensed remotely by a magnetometer. For the case of Triton, what is the time-varying source? For Europa, the time-varying source is Jupiter, and of course, the time-varying magnetic field source at Triton is Neptune. Here we see this animated visual, one to the right, and one of the main advantages that we can see is that it's got a tilt in the magnetic axis defined by this the magenta line with respect to Neptune's spin axis, which is the white line. This creates a time variation at the position of Triton as it orbits. Additionally, even though Triton has a near perfectly circular orbit, it actually has this high inclination actually allows the moon to see different magnetic latitudes of Neptune, and therefore see time variations at the orbital period, or 141-hour period. And that the red streak right there, that's our baseline trajectory that we use, and the trajectory that I use in most of the data in this work. So continuing, if I were to plot the magnetic field as a function of time at the location of Triton, what we see is this figure up here on the right. We see the dominant 14-hour synodic wave and the 141-hour orbital waves. If I were to take the Fourier transform of this particular sequence, what we notice is there's additional tones, and these are attributed to the beats and harmonics of the two fundamental frequencies. Now, each one of these frequencies drives magnetic induction. Drives magnetic induction within Triton by this simple equation. And what we realize is that you can model this by a simple scaled and phase delay response of each one of these driving fields. Again, the amplitude scaling is defined by this AK, where K is defined by it represents the frequency, and the phase delay. And this happens for each one of these frequencies. We talk a lot about the total magnetic moment, which is what we actually observe at Triton. And this is the summation of all these different individual magnetic moments summed together. So I was talking to Jody earlier, and one of the things I like to do in a lot of my presentations is show some visuals, because these things can be quite complicated, this concept of magnetic induction. And on top of that, the Triton-Neptune system itself is kind of quite complicated. So being able to picture these things, I think helps bring the concepts to life and easier to understand. So this total magnetic moment that I was referring to is indicated by the red line, line emanating from Triton that's spinning around Triton right now. And it's associated with this dipolar field, similar to what you'd expect to see for a bar magnet. And these two things are synchronized to the rotation of Neptune, as you can see. The figure over to the right illustrates the total magnetic moment that the total magnetic field that we see. And the lines that are almost horizontal now, the yellow lines are the field lines that connect Neptune through Triton. And the induction response actually, as you can see, perturbs the magnetic field around Triton. And is this perturbation that we look for to look for an ocean. Okay, so in order to best infer the interior properties from a given set of measurements, what we do is we forward model tens of thousands of different interior profiles of Triton and see which ones best matches the data. Up in the upper left shows our interior model. We have a non-conductive mantle, a conductive ocean, a non-conductive ice shelf, and an ionosphere composed of various layers of thickness and conductivity. And this allows us to tailor the profile of the ionosphere if it has any structure to it. And again, I mentioned before, the important reason to model the ionosphere is because it's conductive. So it too will create an induction response that could potentially mask the ocean. So the goal doesn't necessarily become if we can detect an induction response, if we can detect an induction response from that of an ionosphere only model and that from an ionosphere plus ocean model. So we model 51 different ionosphere models from height integrated conductivity of 0 to 100,000 Siemens. And we also model 256 different oceans for each one of those ionospheres, so totaling over 13,000 different models. And our ocean space is defined on the bottom left. Each one of so the ocean conductivities range from 0.1 Siemens per meter to 30 Siemens per meter. And the thicknesses of the oceans range from 10 kilometers all the way to 310 kilometers. The blue dots represent our most likely oceans. The gray dots represent our least likely oceans, but we carry them along to show where the methodology breaks down. Also indicated, there's a little green dot there, and that is what we call our least favorable likely ocean. And we highlight that because it's the hardest ocean to detect in our likely cases, and it defines our boundary and sets the margin we assess in this work. So again, what we do is we can use this software called Planet Profile, initially developed by Steve Vance. And this allows us to model the complex response function at multiple frequencies using this interior modeling method. And here we plot the complex response function in the complex domain, where again the magenta and yellow colored dots represent our ionosphere only models, and the shades of blue represent our ocean plus ionosphere models. And what's important to see here is that there's good separability in this domain, providing indication that detection can be possible. And again, this is the synodic frequency. So what you'll notice is there's some overlap into the right, where these, I guess it's almost an orangish color merges with the blue shade dots. And this is because this is right around a ionosphere height integrated conductivity of about, I think, 40,000 Siemens or so. And this is because at the synodic frequency, that wave cannot penetrate the ionosphere to participate in the magnetic induction in the ocean, and therefore not useful. This is why the orbital wave below is so useful. As you can see, there's complete discriminability between the ionosphere only models and the ocean plus ionosphere models. So using both these waves are very advantageous. Moving one step forward, we can actually model the total magnetic moment at a particular Neptune magnetic phase, illustrated here on the right. And what we see again is a good, what we refer to as magnetic separation between our least favorable likely ocean, this green trace, the green dots, and the ionosphere only models, the magenta dots. But this is not what we measure with the magnetometer. And just provide some additional information as to why we see this separability. So here's plotted the amplitude response of all our 13,000 different models for the 14-hour synodic and the 141-hour orbital wave. The amplitude response is a function of height integrated conductivity of the ionosphere. And as you can see, there's not much difference between the responses and the amplitude for the 14-hour synodic, but there is some in the 141-hour orbital period. But what's more important is the phase response. As you can see in the 14-hour synodic, there's good separability between the magenta and the blue dots for height integrated conductivity less than 20,000 Siemens, but not much above it. And it's because, again, this wave cannot penetrate the ionosphere at such high height integrated conductivity. The 141-hour period shows where the best discriminability is, and this is key to include this particular harmonic in the analysis. So I mentioned before, we don't measure the magnetic moment. We measure the induced dipolar time series with the magnetometer on the course of a flyby. And these simple equations here show the relationship between the induction magnetic field as a function of time to the magnetic moment, which is a three-element vector, mx, my, and mv, evaluated closest approach. It's related to the induction of the dipolar field by a 3x3 dipolar matrix, this D matrix, which we can see here is effectively related to the trajectory. But what's clearly noticed here is in these three traces at the bottom, there's no concept of magnetic separation or distinguishability between the magenta, which is the ionosphere only models, and the blue shades, which is the ionosphere plus ocean models. So what do? We actually shove it into a methodology called principal component analysis. Okay, so why can PCA be used? Well, it first involves investigation the energy involved in the discrete time series. Here again is the total magnetic moment. And what you do is for a total magnetic moment, for using data inversion, you can actually solve for these coefficients. And you're actually throwing away these dipolar coefficients using all the data. But what you can do is if you write out the energy, the discrete time signal energy of the sequence, which is basically the summation of every single sample squared, you can rewrite this in terms of what we call a scaled magnetic moment vector, this M1, M2, and M3. And this scaled magnetic moment vector can actually be related to the induced magnetic moment, MX, MY, and MZ, by a 3x3 scaling matrix. So this writing out the equation in this form demonstrates the ability of data dimensionality reduction, and that's where PCA comes in. PCA is almost equivalent to this, and it's doing exactly the same operation. So I don't have much time to go into PCA. You can look it up on Google and find a whole bunch of information on it. But what's really important to realize is that PCA is a dimensionality reduction tool that's able to find the axes of greatest variability. And these essentially, essentially what we do is we stack all the data, our forward model data, these blue ocean traces and the magenta ionosphere only traces. We shove them all, we stack them together, BX, BY, and BZ as shown here. And then we feed them all into a matrix. And then we perform an eigenvalue decomposition on this matrix, which is just a fancy way of saying we extract the eigenvectors and the eigenvalues of this big, large matrix. Okay, and then what we do is we can use those eigenvectors to project the measurements into a lower dimensionality or space. And that's illustrated over here to the right. Note the similarity, how it looks to the total induced magnetic moment space. And then what we do is when we actually get a noisy measurement indicated by this, this orange trace, what we can do is you can use these existing eigenvectors and project that noisy measurement into the classification space. And wherever this ball lands in this three-dimensional classification space will determine whether or not we have an ocean or not. And we can also infer some characteristics on the ocean properties, the thickness and conductivity as well. Okay, so in order to show robustness against various factors, the first thing we had to do was to show resiliency to the unknown magnetic phase of Neptune. Here we see the magnetic moments, the induced magnetic moments for all 13,000 models. Actually, it's not 13,000 because we're not carrying along the non-likely oceans. Again, the blue here are the likely oceans, and the magenta dots are the ionosphere only cases. And this is just a 2D and 3D projection in space of what these total magnetic moments look like as a function of time or Neptune magnetic phase. So each frame is a different magnetic phase of Neptune. And this just shows the separation between the bounding ocean case and the ionosphere only case. So in PCA, what we do, this is effectively what it looks like, what it's doing to the data above. It's hard to see here in the two-dimensional space. There actually looks like there's some overlap between the ocean models and the ionosphere models in the 2D space. But once you look at it in the third dimension, there's complete separability. And this occurs also for the magnetic moment. But you can see that there's greater separation between the two. These two are plotted on the same scale. And I actually, so again, this is the magnetic separation between the likely oceans and the ionosphere only models, plotted against height integrated conductivity. And you notice we have greater separation for low ionosphere height integrated conductivity. And it's because of the fact that the 14-hour wave, which is larger than the 141-hour wave, can participate in magnetic induction. But I really like this visual. It actually looks like an ocean wave, so it's a little bit ironic. Okay, so we also had to do sensitivity to trajectory. And one might ask, why is the induction response sensitive to trajectory? And it's because of the fact that if you're familiar with a dipole, this induced dipole, the strength of the field is going to be twice as strong as the magnetic pole than it is at the magnetic equator. And if you remember that first visual that I showed you, the magnetic moment actually rotates around the geographic equator, where the field will be 2 times as strong. So it's more advantageous to fly near the geographic equator, where we're more likely to see the magnetic pole. So here are a bunch of different trajectories. The T0 trajectory indicated by the magenta line represents the Triton baseline trajectory. And this was settled upon due to other science investigations as well. But this is right around the just around the geographic equator. And then there's also T1 to T4 trajectories. And what we notice is that the T1 and T3 trajectories are optimal. And that's because they spend the most time around the magnetic pole or the geographic equator, and also where the BX component of Neptune's magnetic field is the largest. The figure over to the right just shows the magnetic separation for each of these trajectories for the least likely or least favorable likely ocean case as a function of height, ionosphere height, integrated conductivity. And we can see this is averaged across all Neptune magnetic phases. So as you can see, the T1 is optimal, closely followed closely by the T3 trajectory. And again, this is all done at a single argument of latitude of 50 degrees. This can be improved by moving to an argument of latitude of 90 degrees, where the 141-hour wave is maximum. Okay, we also show the some resiliency to loss of data. So what happens if there's a full channel outage? What if you lose your BX, BY, or BZ component and multiple components? Well, what you can do is just discard them in the analysis, and the PCA can just eat that up. It doesn't really see this information. It just uses the data as is. So what we can see here is the top one is the BX, BY, and BZ. This is the magnetic separation of the least favorable likely ocean cases as a function of the ionosphere conductivity or conductance. And then the cyan line is, say we drop BZ, which contains the least information. So we basically are able to get the same information out. But as soon as we drop BX or BY, there's a significant loss to the amount of magnetic separation from the ionosphere cases. But even when we have the BZ only and we drop BX and BY, there's still a little bit of separation. Ocean detection is definitely not likely going to occur, but you have some possibility if you can keep the noise low. We also simulated data window outages, where we chop a section of data out of each of the magnetometer channels for a 1 minute, 2 minute, and 3 minute window losses. And you can see the results over here to the right. Again, these are the least likely or least favorable likely ocean cases plotted as a function of height, integrated conductivity of the ionosphere. Okay, so plasma interaction field. This is another big concern of the team going into it. And one of the reasons why we don't think the plasma interaction field due to co-rotating plasma currents will be a problem is because of the fact that due to the complicated geometry, Triton actually spends a lot of its time away from the magnetic equator, where one would expect plasma currents to be at their largest. As we can see over to the right, the white line represents the distance to the magnetic plane. And as you can see, it crosses this plane twice every time Neptune orbits, but when it's at maximum away, it can be at least 12 Neptune radii away, further distance itself from these magnetospheric currents. Another cool thing that is really kind of a coincidence is that during these times where during the times when it crosses this plasma sheet, it's conveniently that the plasma flow angle, which is assumed to be co-rotating with the magnetic equator, that this angle with respect to the magnetic field is furthest away from 90 degrees, where perturbation of the magnetic field is expected to be the worst. And here's just a representative model done by Lucas Liazu and Carol Patty. And this work was just published just a couple of months ago, I think. But just shows the relative strength of the field signatures of the plasma for BX, BY, and BZ. And as you can look at the magnitude, the strength of these signatures are not really strong. So we actually can just treat this plasma interaction field as a noise source, which is really convenient. Okay, so now we do a sensitivity to noise. We performed a Monte Carlo analysis, and here again we only look at the ionosphere only models and the least favorable likely ocean case. And what we do for each one of these models is we perform 1,000 different flybys with 1,000 different noise scenarios. And yeah, I'm trying to think off the top of my head. This is we varied instrument offsets, the flicker noise. We also introduced timing uncertainty, 3 sigma of 1 second, attitude uncertainty, I think it was 1 degree for 3 sigma, and then also positional uncertainty of 10 kilometers, 3 sigma uncertainty. And this just shows you after the, this middle plot shows you the distribution in the air of these measurements in the PC classification decision space. And what we can see is that we expect to see a 3 sigma noise, total noise of about 1 nanotesla. So what we can do is when we get our measurements, we can project them into this decision boundary, or in this decision space. And if it falls on the upper level of the decision boundary, we have an ocean, because in this case, we probably have a least likely ocean if it falls in this white space. If it falls below, it's likely just an ionosphere. Now, what happens when we introduce this, the plasma interaction field shown on the previous slide? What happens is that because this structured noise is introduced to every single one of the models, it actually just simply moves the decision space. But by time of the measurement, we won't know that this is in the data unless we model it. So we can actually, if we just treat this as a noise source, we can just show that as a reduction in our separability in our decision space. And as you can see here, it just biases this space. About minus 0.18 nanoteslas in the PC2 dimension and 0.3 nanoteslas in the PC1 dimension. So as you can see here, plasma interaction fields are not going to be a concern for us. Okay, so again, this 1 nanotesla field that we determined from the Monte Carlo simulation gives us a figure of merit of detectability of oceans. So what we do here is we plot the magnetic field contour, separation contours for our ocean space, ocean conductivity versus ocean thickness for 4 different ionosphere height integrated conductivity. From the left is 10,000, 30,000, 50,000, and then 80,000. And what you can see here, you can see there's a dotted line surrounding the our most likely oceans, and this is the region we actually care about. Obviously, for height integrated conductivity of 10,000 Siemens, there's great separability between the models. But as we move higher and higher in conductance, the separation goes down, and that's because the 14-hour wave cannot participate in magnetic induction in the ocean. Therefore, we have less separability, so it's going to be harder to detect. However, we notice that there's no overlapping red contours within our likely ocean cases. Therefore, we can detect all these oceans with 100% confidence. But now, what happens when we move the magnetic phase to 120 degrees? We pick 120 degrees because that's the least favorable. And what happens is that at this particular phase, the 14-hour synodic period actually adds destructively with the 141-hour period, therefore reducing the effect of the magnetic induction signature. As you can see, the height integrated conductivity of 10,000 Siemens, we get really good separation. But as soon as we move to 30,000 Siemens, the separation really drops. In fact, it gets down to 2 nanoteslas in our likely space. But as the further we go up, the less the 14-hour wave participates in magnetic induction. And over to the right then, from 50,000 Siemens up, the traces look relatively the same because it's purely the 141-hour wave that's performing magnetic induction in the ocean. And then just to complete the circle, we did another one of 240 degrees magnetic phase. And here, again, we have really good magnetic separation and can distinguish ocean plus ionosphere from ionosphere only model for all these different cases. Also, I only have a couple more slides left, so I'll try to wrap up. But I have just real quick, we did the, this presentation was mainly for single pass, but we also investigated how the methodology reacts to multiple encounters. And what we can do is we can actually stitch a bunch of these trajectories at different arguments of latitude together and see how that results in a multiple encounter mission. And what happens is that, so this bottom, in the figure to the right, the bottom figure represents the least favorable likely oceans for a single pass, an argument of latitude of minus 90 degrees. Then we stitch the 45-degree argument of latitude trajectory data into this. And then we get, as you can see, we see a slight increase in magnetic separation and so on, up to 5 different trajectories. So what does this look like? This actually allows us to perform some kind of characterization on the ocean using this methodology. Here are the same figures, the same conditions. For this top row represents one flyby with an argument of latitude 90 degrees, but for 4 different ionospheric height integrated conductivities, 10,000, 30,000, 50,000, and 80,000. So this shows you what kind of characterization is possible for single flyby missions for 3 different oceans. Ocean 1 represents a conductivity of 6.5 Siemens per meter with a thickness of 70 kilometers. Ocean 2 represents conductivity of 4.5 Siemens per meter and a thickness of 170 kilometers. And Ocean 3 is 2 Siemens per meter with a thickness of 250 kilometers. And as you can see, the contours, you want these contours to be tightly constrained. But as you can see, characterization is not really possible with the using our 1 nanotesla metric. A little bit of constraint can be possible at 10,000 if the height integrated conductivity of the ionosphere is less than 10,000 Siemens, but it's likely not going to be that low or below that. So what happens when we go to 3 flybys? Well, what happens is we get more information, and the data actually can further separate these ocean cases. So we see a really tight constraining of these ocean properties for 3 flybys. And similarly, we go to 5 flybys, even tighter bounds. So a multiple flyby mission can definitely provide constraints on the ocean thickness and conductivity. And we can also infer properties of the ionosphere at height integrated conductivity as well. Okay, so with that, I'm just going to leave you with 2 more slides, just 2 visuals I've done for the flyby of Triton Pass. But anyway, subsurface detection is possible at Triton on a single flyby, despite the confounding factors as plasma interaction fields, the intense ionosphere, uncertainty of Neptune's rotation period, spacecraft and instrument noise sources, spacecraft uncertainty, and data loss. And we also introduced a novel ocean detection methodology, which can be applied to multi-pass orbiting mission concepts. And this is applicable to any other icy moon in the solar system that resides in a strong time-varying magnetic field. So that with that, I will take any other questions, and I'll let this simulation play for a couple times, and then I'll stop it if it becomes distracting. So thank you.
Awesome. Thank you so much, Corey. I really like the graphic on the previous slide that sort of shows what the spacecraft would be seeing as it flies by both objects. That's really awesome. Let's see. So I think that there's a couple questions in the chat, and so I can voice them, or if people would like to unmute themselves and speak up. This seminar is very much a discussion-based conversation, and so if people would like to ask their questions, you can kind of raise your hand and I'll call on you, or I can just read them off of the chat. So whichever one you're comfortable with. I think a couple of the questions in the chat got answered already. And so yes, the talk is being recorded. It'll be uploaded onto the same website that you that you registered for this talk. In fact, I'll put that in the chat now just so that people have access to it. So previous recordings and registering for future events can all be found at this website. So this particular talk will also be uploaded there. So let's see. So I think first question is from Dick. Is tomography possible from multiple flybys?
Say the question again.
Is tomography possible from multiple flybys?
Yeah, I would say it would be. I'm not an expert specifically in that, but I think it definitely would be. Multiple encounters gives you, for magnetic induction specifically, it allows you to see the different, different conditions of, the system, namely different arguments of latitude, different phases of Neptune. So it could definitely provide more information, I'd say.
Okay, great. Let's see, the next question is from Una Schneck. This is, how large do you model the ice shell above the ocean?
A great question. So the ice shell, I think what we do is we use a fixed hydrosphere layer of, I forget the number. I see Carl online, he might remember. I think it was 370 kilometers, I think, if I remember correctly. So we fixed that to make it the hardest to detect oceans. So the ice shell is variable because we have different ocean thicknesses that we model, but we model the seafloor as being fixed. So the thickness is varied with respect to the seafloor depth. And I think that was 370 kilometers, if I remember correctly.
I think
It's been a while since I did this.
It was 340 based on sort of published range of estimates, mostly from Francis Nimmo and his group. As the output.
That sounds about right, Carl.
And we did look at thinner ones briefly, but they just turned out to be easier.
Thanks, Carl.
Alrighty, yeah. So for anyone else, feel free to raise your hand, or you can post in the chat. I've got a quick question while people are sort of composing their thoughts. So I was curious if this sort of technique, and I'm asking this mainly because I know that you're also on Europa Clipper. Is this the sort of thing that you could also do for Europa Clipper, sort of to attempt a proof of concept, perhaps to constrain uncertainties in the models, or would things not really be transferable?
Yeah, great question. Yeah, definitely applicable to Europa Clipper. We've actually applied this to Callisto and shows that it's really promising right now. One of the problems with the Europa system is the plasma interaction field. And I mentioned here, we just treat them as a structured noise source. But for Europa, you can't do that because the interaction fields can be quite large. So currently, one of the techniques that's been used is, a data inversion analysis, which is a very good technique. But the advantage of that is you can actually, what you have to do with that is you also have to model the plasma and then remove it prior to doing that. So you could do a similar thing with this methodology there. And again, there are some passes where plasma interactions are minimal because of the distance Europa is from the plasma sheet. And another thing that I mentioned earlier in this talk is that you can actually discard channels that are compromised by plasma. This loss of BX, BY, or BZ. You can meticulously remove a channel and process if it's contaminated, and then perform the analysis that way. And that's what we're doing actually with the Callisto data, which is shown to be really promising right now.
Okay, great. Let's see. So this one's a long one. So Nisha, if you'd be willing to unmute and ask, I think there's a couple questions in here. Yeah. Okay. Thanks.
I worked on similar work for Earth, so I find this so interesting, and I really liked your presentation. I was just getting a little mixed up with the noise calculations. Were you using Monte Carlo to determine noise of the signal that you get from the PCA? Was the idea there, I know you were comparing with and without the plasma interaction, but was it also just to provide an estimate of the noise of the actual PCA signal itself?
Yeah, good question. So yeah, so each one, so if you look in this decision space up on the upper left, the green dots are where the dots should land, and what our forward modeled space, basically in the principal component space. And each one of this fuzz that we call it around it, each one of these little dots around it is a corrupted flyby measurement with multiple sources of noise that we added to it. And then what we do is we forward model that noisy time domain signal and project that into that space, and that's where it lands. And looking at the distribution of that fuzz shown here on the second, the middle two columns, shows us the distribution of the air one expects to see in this principal component space. In both of this case, we see 0.34 nanotesla 1 sigma. So we just go with a 3 sigma spread, roughly about 1 nanotesla, to show our error. Does that make sense?
I think so. Yeah, thanks. There's a lot of material here.
Yeah, it's cramped. I apologize. I try to throw as much in there as possible, but we do have a paper under review that's coming out hopefully soon. So hopefully it's all explained in that too.
Then one other thing I was wondering was just when you were estimating a single pass, I know you showed the different trajectories, and I was just curious, like how the different passes might vary in terms of the amount of data that you're using for this calculation, especially like how the total time span of the pass might relate to the like magnetic periods of interest here.
Yeah, that's another great question. One of the reasons, one of the reasons we have this data in the first place is because what happens is that the orbital magnetic wave, the 141-hour period, is actually maximized at an argument of latitude of 90 degrees or minus 90 degrees down here. So what we did is we have these trajectories, and the amplitude of that wave is 2.6 nanoteslas, and that's where we find the greatest distinguishability between the model classes. So we want to be near one of these areas. But we also, one of the baseline was flying over here. The original baseline when Triton first developed was near 0 degrees actually. But there's least information. There's 0 amplitude in the BX component. Sorry. It's a little confusing because there's BX and BY, and both of them have different amplitudes, but there's minimal information at 0 degree argument of latitude for the 141-hour period. So you want to capture all these different phases of the orbit, and what you get for free is the rotation of Neptune. So the different phases of this synodic period, you get that automatically just by arriving at a different time. Hopefully that it's not a coincidence that you arrive at the same phase, but most of the information is in the orbital wave. So these high argument of latitudes.
Cool, thanks.
Yeah, if there are any more questions, yeah, feel free to raise your hand or post them in the chat. I actually have one more question, if that's all right. So I was curious if there are any instruments that could be, whose data could be combined with measurements from a magnetometer aboard a spacecraft like Triton to sort of improve the accuracy of its ocean measurements, or if this is sort of more of a standalone measurement, standalone instrument kind of thing.
Yeah, great question. It's related to the, let me go back here, this guy. So a plasma instrument, to measure and be able to model the plasma. So we treat it as a noise source here, right? A structured noise source. But if you were able to measure the plasma interaction fields and model them precisely, I know Lucas and Carol do. That's what they do really well. So if you were able to do that, then you can reduce this offset variation. Because what you do is, like I mentioned before, you model it and then you remove it from the data set, and then you process it like that. And as you can see here, this having the plasma as a structured noise source actually reduces the separation distance between some areas of your model space. So you wouldn't have that if you were able to accurately model the plasma. I know there's some uncertainty in modeling the plasma, but it still would be in the right direction of improving the effect.
Okay, great. Thank you. Let's see. So we've got the last few minutes of the seminar, and so as is tradition, I'm going to flash up a quick slide of sort of community news, updates, things that might be relevant to people who are attending this talk. And so this is sort of a place, you know, if you have something that you'd like to advertise to the community, absolutely feel free to shoot me an email with the info. I'd be happy to add it to this. So we've got the next Neptune Triton System Seminar Series coming up in a month from now. So it's going to be the second Tuesday of February. And we've got Dr. Candy Hansen presenting over some work on Triton that she published last year. And the link to register for that and for any of the seminars in this series is at that neptuneodyssey.jhuapl.edu/events. And I'll post all of these links in the chat too. In fact, I'll just do that right now so that people can click through them while I'm talking about them. But so that one is sort of the most important one. So you can register there. You can also sign up for the listserv, and the listserv is sort of intended to be sort of a reminder of registration. So I'll send sort of updates to whenever we get new speakers, whenever registration opens for seminars and stuff like that. And so feel free to sign up. If you go to that website and you look under the Stay Informed section of the webpage, you can kind of sign up for the listserv there. And so then I kind of also wanted to just plug that there's quite a few number of conferences that are coming up. So the SBAG meeting is very soon, in a couple weeks. LPSC abstracts are due today. So make sure you get your abstracts in. And then EGU has an Ice Giant system exploration session that has abstracts due tomorrow. I thought people in this group might be interested in. AbSciCon also has tons of really great sessions that are relevant to this community. So those abstracts are due sometime next week. And then the OPAG is having positions open for their steering committee. So if you're interested in that, feel free to go there. And I just saw in the chat, thank you, Krista. Okay, yes. And then the OPAG meeting, I'll make sure to add that also to the next few community news PowerPoints that I make. So that's good. Right. So OPAG, is there a registration deadline, or is it kind of open up until, I'm assuming it's probably similar to SBAG where the registration is up until the start of the conference. So hopefully that's the case. Right. So if anyone would like to add something to the community news, feel free to send me an email. I'll put my email in the chat here, or you can respond to me through the listserv. And thank you all so much for joining today. Thank you again, Corey, for an excellent presentation. And I hope you all have a wonderful Tuesday afternoon. Thank you so much.
Thank you.
Thank you, Jody. Nice presentation, Corey.
Thanks, Al.
Thanks, Corey.
Done.